In this example, we'd like to calculate the center of mass of the laminar region that's given by this this portion right here, upper half disk. So this is our region D with this density function. And so in this situation, A is obviously the radius, so A is a positive constant. And this number K, this K is also a positive constant. But it's a constant, so we don't have to worry about it. But the rho is then proportional to x squared plus y squared square root. The proportional constant is K. So we want to try to find the center of mass. We've done an example of this already, so we know exactly what we need to compute. We need to compute our moments, m sub x, m sub y, and we need to know the actual mass, lowercase m. So let's write out first the mass, so the lowercase m, the mass of the region. We can compute that, and then we can go from there to compute the actual moments. So the mass, remember, is the double integral over our region D of our density function. So it's going to be the double integral over D of K times square root x squared plus y squared dA. And at this point, we think to ourselves, man, this really feels like we should be using polar coordinates for a couple of reasons. Number one, this region is a circle, right? A circle in polar coordinates can be built the following way. This upper half circle, I should say, we can let the radius vary from 0 out to A. That'll trace out this line segment in the direction of the angle theta equals 0. And then our theta can just pick up this little segment and zing it all the way around from 0 up to theta equals pi. Okay? Now, there's another thing that makes this feel like it should be done in polar coordinates, and that's this function right here. Because remember that the square root of x squared plus y squared, the rectangular function here, this is just equal to r in polar coordinates. Okay, so that's going to make our rho, our density function, as a function of r and theta, just be equal to k times r. So there's a nice density function right there. The other thing that we have to remember if we're going to use polar coordinates is that we have to properly change our area element. And hopefully we remember that the dA in polar coordinates becomes r, dr, d theta. We need this extra r right here. So let's make the appropriate changes and compute this mass as a polar integral. The integral now goes, the theta goes from 0 to pi. This is a polar rectangle, by the way, so this is going to be very nice. The radius goes from 0 to a. Remember, a is a constant, so we don't have to worry about that too much. And then in here, our density function becomes k times r, and our dA, or area element, becomes another r, dr, d theta. K is a constant, a is a constant, r is obviously one of the variables. There are no thetas here. So this is a separable integral. The k can come all the way out. The integral with respect to theta is just integral of 1 d theta, or just d theta. And the integral in the r direction is r squared dr. These are all very simple Calc 1 integrals. We can compute these. We get that the mass of this region is k times pi times a cubed over 3. So you should be able to compute these very easily, and then we end up with a cubed times k times pi. It doesn't matter what order we put these in. These are all constants over 3. So this is the mass. This is the mass of our semicircular region, our disk, half of a disk. What we need to do now is compute the two moments. Remember, the moments, m sub x, is equal to the double integral over the region of y times rho of xy dA. All right, same thing, the moment with respect to y is the double integral over the region of x times rho of xy dA. And if we're going to use polar coordinates, which was a good idea here, and it still is a good idea, then we need to remember how to treat the x and the y. Our x becomes r cosine of theta, our y becomes r sine of theta. And so these changes need to be made when we compute our moments. All right, I'm going to get a clean sheet of paper here to compute these two moments, but they are just going to be the integrals of the same integrand, but times this extra factor here. So let's get some clean space here. And our moment with respect to x is going to be, let's do the moment with respect to y first. The this is going to be the double integral of x times rho of r theta, I'll write it this way, times dA. So this is the integral from 0 to pi, integral from 0 to a, r cosine of theta, times k times r, times dA, which is r dr d theta. Okay? So again, k is a constant. Now we have a theta term. We also have these r terms. This is still separable though, so this can be separated out to be k times integral from 0 to pi cosine of theta d theta times integral from 0 to a r cubed dr. All right, k is obviously a constant. The integral from 0 to pi of cosine, you can maybe think about this yourself geometrically, but I'll work this out. But think about how you could do this geometrically without writing anything down. This one becomes, antiderivative is obviously sine of theta, and we plug in 0 and pi. And over here, this becomes just a to the 4th over 4. So, simple integral there. But here, sine of pi and sine of 0 are both equal to 0. So this becomes k times 0 minus 0 times a to the 4th over 4, and of course that's 0. So the moment with respect to y is just 0, and that's because of this extra term in the theta direction that wasn't there when we computed the mass. All right, but if m sub y is 0, that means that our x bar, our center of mass in the x direction, remember, is m sub y over m. This is just 0. So the coordinate for the center of mass has x value 0, which means it lies on this y-axis. So the center of mass is somewhere on the y-axis. Now, because of the symmetry of the region, we might have guessed that, but it also has to do with the symmetry or the simplicity of the density function. Okay, the density function is also symmetric. So you can't just assume that because the region is symmetric that the center of mass will be on this y-axis, and that's not always the case. But for this density function, it is. And we are left with still charged with computing the moment with respect to x. And so this is the integral of y times rho of r theta dA. And it's going to be very, very similar, except y is not r times cosine, it's r times sine. So this is integral 0 to pi, integral 0 to a, r times sine of theta, times k times r dr d theta. Again, it's separable. Again, k is a constant. Again, it's very, very similar, except the difference now is that we're integrating sine of theta from 0 to pi. This will not be 0 because sine is positive in the entire upper half plane. Cosine goes from positive to negative. It has symmetry. It's cosine, sorry, is an even function. So it's an even function, but it's odd with respect to the interval from 0 to pi. And then this integral from 0 to a of r cubed dr, we will just work this out. This becomes k times negative cosine of theta from 0 to pi times a to the 4th over 4. Again, simple power rule right there. Now when we plug this in, cosine of pi is negative 1, cosine of 0 is 1, and so this ends up being k times negative 1 minus a negative 1. So this becomes 2, right, times a to the 4th over 4. So this is 2k a to the 4th over 4, or just k a to the 4th over 2. All right, this is the moment with respect to x. Remember our y bar, its coordinates are m sub x over the mass, m. And so this is going to be k a to the 4th over 2 divided by the mass. Remember our mass was this, a cubed times k times pi over 3. So a cubed times k times pi all over 3. And then we can multiply by the reciprocal here. We end up with 3k a to the 4th all over 2a cubed k times pi. The k's will cancel, and the a powers of a will cancel. It will leave one a on top. Remember, a was positive, so it's okay to cancel it. And the coordinate of our center of mass in the y direction is then 3a over 2 pi. All right, and remember, pi is a little bit bigger than 3, so this factor is a little less than 1, a little less. A over 2 is half the radius, so this is a little below halfway, the halfway point on the y-axis to a, to the radius. All right, and so what we have here, it's a little less than a over 2, so here's a over 2, it's a little less, it's maybe right here, and this is our center of mass, x bar, y bar. Again, the coordinates for x bar, y bar are, for this example, 0, and then 3a over 2 pi.